Okay, hello. So there are few of the structures which I would like to discuss in this video. So let us take the monomers. So in this case, the monomers that we have taken is hexamethylene diamine and adipic acid. Okay. So if you do the reaction of these two monomers or structural units at 553 Kelvin and high pressure, here you will be getting nylon 66. We have already pre-written the structures. Now in this case, what happens is that you basically have to remember whenever there is COOH in the structure, you have to eliminate OH from there. It's not that it is basic or acidic, we're just eliminating OH to make the structure look easier. Okay, so similar way, if you are eliminating OH from one of the structures, you have to eliminate H from the other structure. Okay, so what I'm trying to say is that you eliminate actually H2O minus H2O. Okay, so that means from this cone also H will be eliminated, and from this cone also H will be eliminated. So that means the structure that we'll be getting is that will look something like this. That is, you have removed, and from here you have removed H from here, then the structure will remain same. In this case H will be gone, in this case OH will be gone, so this C double bonded O carbon will be connected to nitrogen and it will look something like this. Okay, so I'm just making the structure look easier. C double bonded O, then here. Okay, so here we'll be dealing with a large number of molecules, so that's why we write here N. N means large number of molecules. So sometimes you may see that the structures have N in front of the monomers, so that N means large number of structures. Okay, so if you treat hexamethylene diamine with adipic acid, you will be getting nylon 66. Now in this case, nylon 66, this 66 designates the number of carbons. Okay, number of carbons in their particular monomers. Okay, we are saying nylon 66 because in hexamethylene diamine you have 6 carbon. Similar way in adipic acid you have 6 carbon. So 2, these 2, then 4 of them. Okay, so that is about nylon 66. Then the uses, please refer to your book. Okay, then for this here in this case we are eliminating H2O. So since we are eliminating small molecules like H2O, this falls under condensation polymer, or it is also known as step growth polymers. Okay, you can see your notes. Then you can also see that these two will fall under copolymer, because here we'll be using two kinds of monomers. If they are using only one type of structure, then it will fall under homopolymer. If you are using two kinds of structures, it will fall under copolymer. Okay, so in this case we'll be doing more about the structure. Let's do some of the structure. Let's say how will you prepare nylon 6? Okay, so from the name itself, nylon 6, so that means 6 is there. So starting material or the monomer will have 6 carbon attached to it. So in this case you will have a structure which is known as caprolactam. So the structure you can do it easily like this. First you draw sort of cyclohexene structure. Of course this is not caprolactam. Then what you do is make one of the carbon to be double bond and insert here N. Okay, and H. So you'll get a structure like this: CH2, 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 CH2. So you can see it's 1, 2, 3, 4, 5, 6, 6 of them. Okay, so this is known as caprolactam. So similar way, what you do is you can see this structure. Here was this connection, okay, N and C double bonded O. So here also you cut between N and C double bonded O. So you'll get a similar structure which looks something like this: NH, CH2, 6 of them, sorry 5 of them, C double bonded O, then okay. So this is the way you'll prepare nylon 6. So you can search the uses from the book. Okay, so that is about caprolactam. The next is about two monomers again. So you take these two monomer, that is 1,3-butadiene and styrene. So you'll be getting as the polymer which is known as Buna S. Okay, Buna S. So in this case what you do is this double bond is going to come over here. So the single bond will become double bond, the double bond will become single bond. Similarly this double bond will come sort of here. So this, there will be a bond between this CH2 and this CH2. So you'll get a structure that looks something like this: CH2, single bond CH, double bond CH, then single bond CH2, then CH2. Okay, then after that here this will be this was a double bond, so it has to be a single bond. Okay, CH. Then this structure, just write it up better, it will look more systematic. Okay, then close the bracket, then N. Okay, so this sort of structure you'll get, which is known as Buna S. So the starting material in this case is 1,3-butadiene and styrene, and the polymer that you'll be getting is Buna S. Okay, so this falls under copolymerization and also falls under synthetic polymers. Okay, so that means the double bond will become single bond, the single bond will become double bond. Okay, just for this sort of structure in here, don't make a double bond over here. Okay, basically what we are trying to do is limit the bonds of carbon to 4. So if you put a double bond here, it will be 5. So we are making here 1, 2, 3 and 4. Okay, so limit the number of bonds for carbon to be 4. Then similarly you can do it for, let's say, this number 5, number 4. It's a similar sort of structure. Okay, so you can start for this. This is called chloroprene. Okay, so what you can do is this double bond will come over here, as you can see from the product. Then this will become a single bond. However, you can see all the carbons will have always 4 bonds. Okay, so similar way for this two polymers, the product obtained will be Buna N. Okay, so the structure will look something like this. Just satisfy the number of bonds for carbon and you will get the structure CH, then here CN. Okay, so you can see the similarity between Buna S and Buna N. The structure, the extra structure will always be up. Okay, then thank you. If there is any problem, please let me know. For the other structures also I can make, but you try for yourself. Okay, thank you.